Hello, this is Mr. Ezra. Today we are going to talk about piecewise functions. If you're in my Algebra 2 class, we are in our final unit of Algebra 2. It's very exciting. And the first topic that we're going to cover is something called piecewise functions. When we are graphing piecewise functions, we need to understand that the function is going to behave differently for different parts of the domain. For example, in this part of the domain where x values are less than -2, this function will follow this linear pattern of x plus 2. When the x values are greater than or equal to 2, it's going to change and it's going to look a little bit differently. Before we get to the graphs, let's just look at evaluating. So you can see I've kind of color-coded this to kind of help me out. If I want to evaluate f of x for this piecewise function where we have a first part for all x is less than 2, and a second part for all x is greater than or equal to, for x equals 0, the first thing that I have to do is to decide which of these two groups does this value for x belong. Is it less than 2 or is it greater than or equal to 2? And it is in fact less than 2. 0 is less than 2. So when I'm evaluating this, when I'm finding f of 0, I need to make sure that I choose the x plus 2 version because 0 is less than 2. This is the function or the part of the function that I am going to use. So 0 plus 2 is 2. F of 0 is positive 2. For x equals 2, if I'm evaluating f of positive 2, I'm going to plug the 2 in to the part of the function where the x values are equal to 2, and it's right here. So 2x plus 1 is the one that I choose. 2 times the x value of 2 plus 1. Well, 2 times 2 is 4, and 4 plus 1 is 5. And then finally, we've got evaluating for x equals 4. So what is f of 4? Well, 4 is greater than 2. So I choose the 2 times x plus 1, which in this case would be 2 times 4 plus 1, which is 8 plus 1, or 9. So when you're evaluating, you have to find what part of the domain your x value fits into before you evaluate. On the graph, there's a few things for us to talk about, a few things for us to think about. Number one, the function is going to behave differently for all values of x less than -1. That means that when I'm evaluating this function, when I'm getting some xy pairs to graph this line, -1 is one of the ones that I have to test. And I might choose a few x values that are less than -1, like -2 and -3. I'm going to plug these x values into my x plus 1. -3 plus 1 is -2. -2 plus 1 is -1. And -1 plus 1 is 0. And I'm going to plot these values, these ordered pair. -3, comma, -2. I put a dot on the graph. -2, comma, -1. I'll put a dot on the graph. But when I get to this -1, comma, 0, since it is less than -1, it is not equal to -1. And what that means is I'm gonna have to put an open circle on -1, comma, 0, because -1 is not technically on the domain here, but the function travels up to it and stops there. So for all x values less than -1 means that all of these x values are good, forever to the left, down to the left, but this one is not included. For x greater than or equal to -1, I'm going to use a closed circle there because I want to include that -1 value. So again, because that's one of the boundaries, what I want to do is make sure that I include -1 as one of my x values, and then I want to choose a few x values that are greater than -1, like maybe 0 and 1. Here I have a different function. It behaves differently. -x plus 3 is my function for all x values greater than or equal to 1. So I plug in these three x values that I've created into -x plus 3. -1 is positive 1, and 1 plus 3 is 4. -0 plus 3 is 0 plus 3, or 3. And -1 plus 3 is 2. So I'm going to graph -1, comma, 4. Because of the or equal to, I use a closed circle here. 0, comma, 3, and 1, comma, 2. And these should be in a straight line because these are both linear functions, but this one is going down to the right forever. So what's happening here is the left side of the graph is behaving differently than the right side of the graph. Technically speaking, all of my x values are being used because this spot right here, although it's not part of this line, that y value is part of the other line. So there's no break in my domain. My domain is still all real numbers. But my range is not all real numbers. There is a highest point on the graph, and there are y values on the graph below that highest point, but there is nothing above a y value of 4. So I want to remember range, you start at the bottom. So the bottom would be negative infinity because we've got arrows down. Negative infinity, and the highest y value is 4. So I would say parentheses, negative infinity, comma, 4. And because 4 has a closed circle on it, it is included as part of the range. You use a bracket on it. All right, so point of discontinuity may be a new term for you, and all that really means is this graph is not continuous. As I travel from left to right, there is an x value where it jumps and it doesn't keep going. It's not continuous, it's discontinuous. So that x value for which this graph is discontinuous is x equals -1. And you can just write it that way, that the x value of -1 is where there's a break or a gap in the graph. All right, we have another, and this time I have already filled in the graph, so I chose some x values greater than -1, but because -1 is a boundary here, I'm going to use an open circle, but I do want to include it as one of the x values, and I need a few that are greater than -1. And for x less than or equal to -1, I want a closed circle on that -1, and I have to use -1 because it is a boundary there. So let's graph the green part of this function. I've color-coded green is the first one, kind of that maroony red is the second color. So -1 comma -5 is down here, put a little dot for that. Now it is an open circle, so instead of a dot, I want to make sure that I put an open circle because the function doesn't exist here, but it is a boundary and I need to list it. -1 comma -1, 3 comma 3. A common question I get from students is, how did you choose those x values? And I know that I have to use -1. It's a boundary, but I choose any two numbers greater than -1 that I want to try to get an idea of what the function looks like. Technically, to make a straight line, and this is linear, you need 2 points, but I like to have 3 just to make sure that I'm doing things correctly. Let's switch gears to the other function. -2x plus 1 is for x values less than or equal to -1. So this one is going to be a closed circle on -1 comma 3. And then I've got one value less than that at -2 comma 5. And I didn't choose any others. Usually, I said I like to get 3, but unless I use a decimal, I'm off of the graph that's provided for me. So I just chose those 2. Now, what is the range here? Do I have y values forever up and forever down? And I don't. There's a lowest point on the graph. The lowest point is a y value of -5. And I'm going to use parentheses there because -5 is not included. That open circle means it's not included. It just starts there. And then I go up forever towards positive infinity. Where is there a point of discontinuity? Where does the graph jump? Where is it discontinuous? Right here, from left to right, this stops, there's a big gap, and it starts again down here. So -1, or x equals -1, is the point of discontinuity. Where is this function increasing? Well, it's decreasing to x equals -1. It starts increasing at x equals -1. So from -1 to forever, which we use infinity to represent. All right, this one is a little bit different in that the domain goes from -1 to 3 for the first part of the function, and from 3 to 5 for the second. So when I have a less than or equal to, or equal to, I use closed circles. So for this -1 x value, I'm going to use a closed circle. For +3, I'm going to use an open circle. And in the second function for an x value of 3, that's going to be a closed circle, and for 5, it's going to be an open circle. So I again have color-coded green and maroon, and we're going to start with a boundary of -1, something between -1 and 3, and a boundary of 3. I've already plugged these into this function, so when I have f of x equals x, and x value of -1, x equals, y equals, remember this is like f of x or y equals x, so x equals -1, y also equals -1. If x equals 0, y also equals 0, and 3, 3. So I'm going to graph those. The -1, -1 gets a closed circle. 0, 0 is just along the way. But 3, 3 is a less than. So that is going to be an open circle, and that is a boundary. So I can connect those dots. Now, Mr. Esra color-coded these, but then forgot to switch the pen color, so I'll do that right now. And then I'll connect the dots through there. So this function has an endpoint here and an endpoint here. One gets a closed circle, one gets an open circle. When we switch to the other function of x minus 1, that's for x values that are between 3 and 5. So I have already plugged into x minus 1, 3, 4, and 5. I need my two boundaries of 3 and 5 and something between them. 3 minus 1 is 2, 4 minus 1 is 3, 5 minus 1 is 4. So I get 3 points that I can graph for this part of the function. 3, 2 is right here, and it's closed circle. 4, 3 is right here. It's along the way, just a little dot. And 5, 4, 1, 2, 3, 4. This is going to get an open circle because it's less than x equals 5. And I'll connect these dots through here to get something like this. So this function looks kind of odd. We got two little kind of almost parallel parts of linear functions. What would be the domain? Well, in this case, there is a leftmost x value of -1, and it is included. And as I travel along, I have x values on this part of the function to +3, and it picks up again with 3 all the way to 5. So from 3 to 5 is the second part. So I've got from -1 to +5. And the 5 is not included because of the open circle, so it gets a parentheses. The range is also limited here. My lowest y value is -1. It is included, right here, -1. It is included. And I have this function going up, up, up until I get to a y value of 4. And that, because of the open circle, is going to get a parentheses. The point of discontinuity, where does this function jump? Where is there a break? And that is at x equals +3. We got another function. This one has 3 parts. It's going to behave 3 different ways. First, the function is going to be equal to -x for all x values less than -1. So when I find x values to plug in here, I'm going to choose 3 of them, and one of them needs to be -1. And the other 2 need to be less than -1. So I chose -6, -3, and -1. I plugged them into -x. -6 is +6. -3 is +3. -1 is +1. So double negatives cancel out, and that leaves me with the graph that goes through -6, 6. It goes through -3, 3, and it stops at -1, 1. And because it has less than, I must use an open circle on that point of -1, 1. Now, this function is forever to the left of x values of -1. So that less than means I have an arrow on the left. The function switches to something new from -1 to +2. So I need both of those boundaries as x values, and I want to choose something between them to make sure that I get a good straight line. I basically have a function that is equal to -2. So whereas the top one was y equals -x when x is less than -1, this one is always equal to -2 no matter what the x value is. So these 3 x values, it really doesn't matter. The function's always equal to -2. I pay attention to my signs. It's less than, negative 1 is less than or equal to x. So I use a closed circle for negative 1 comma negative 2. 0 comma negative 2 is on the way. But because of the less than 2, I have to use an open circle on 2 comma negative 2. What you'll notice is this is a horizontal line between the x value of negative 1 and an x value of positive 2. The function changes a third time to be y equals 2x. So 2 has to be an x value here because x is greater than or equal to 2. And I choose another x value or 2 that is greater than 2. So I chose 4. 2 times 2 is 4. 2 times 4 is 8. So I'm going to graph those 2 points of 2 comma 4. Closed circle because of the greater than or equal to. 4 comma 8 is right about here. And because it's greater than negative 2, it keeps going through that point forever and up and to the right. So the domain and the range are going to be a little bit trickier here because I have 3 parts to the piecewise function, the first piece, second piece, and third piece. So as I follow my domain, I have x values forever. Even though there's a point of discontinuity, the domain is not interrupted because negative 1 is on the graph, as is positive 2 here, and forever to the right. So my domain is going to be all real numbers. The range is a little trickier. For the range, this negative 2 down here is on the function and it is included. But it's just down here by itself. There's nothing above it or below it on the function right near it. The next thing that I get to going from bottom to top for the range is positive 1. So I'm going to union this y value of negative 2 with the y value of positive 1. And because there's an arrow up here and over here as well, this function has y values up towards infinity. So negative 1 comma infinity. The 1 gets parentheses because of the open circle. Infinity gets parentheses because it always gets in parentheses. Infinity always gets in parentheses. There's actually 2 points of discontinuity. We have a point of discontinuity at x equals negative 1. And we have a point of discontinuity at x equals 2. Those are, remember, the breaks in the graph where it jumps. All right, guys, hopefully you're getting the gist of things now, but I wanted to include one more example of graphs at this point because often these graphs are not all linear, and all the examples we've had up until this point, they have been straight lines. So what about examples where you have something that is a quadratic or something else that's different? And while we have talked about how to graph quadratics and polynomials and all these other functions by looking at the characteristics and trying to graph them, or using your calculator. I mean, you could plug in y1 equals negative x squared and get some x and y values from your table. And you could plug in y2 equals x plus 3 and get some x and y values for that one from your table. Just make sure that this one is x values less than 2, and also include 2 because it's a boundary, and that these are all 2 or greater. But you have to get these combinations of x and y so that you can get them onto the graph. And this one, you'll notice, is going to be curvy because it's a quadratic. So negative 2 comma negative 4, negative 1 comma negative 1, 0 comma 0, 1 comma negative 1, and 2 comma negative 4. Now, because of x is less than 2, I need an open circle for an x value of 2. So I'm going to make sure I put my open circle right here. And this guy kind of curves down, doesn't it? It's up and down, and it keeps going forever to the left. So I'm going to put an arrow over there because it's less than 2. X values less than 2 are going to keep going down on this function to the left. It changes to a linear function for x values greater than or equal to 2. So at 2 comma 5, which is about right here, I can use a closed circle. 3 comma 6, 4 comma 7, I end up with a linear function. And again, I start at here and I go forever to the right for greater than 2. I have a domain of all real numbers. Even though there's a point of discontinuity, that x value is still on one of the two functions. The range is a little bit different. I have an arrow down, so my range starts at negative infinity. And it stops at a y value of 0 right here. I then have a gap between 0 and 5. So I want to pick back up by saying union 5 to positive infinity, because y value up arrow means y values are on this function forever up towards infinity. Remember, because of the dot here and the dot here, both of those should get brackets. They're both included. This dot's included and this dot's included. So both the 0 and the 5 should get brackets. There is one point of discontinuity at x equals 2. That's where the function jumps way up here and starts to behave differently. All right, let's switch gears really quickly and look at a few word problems. You are making class t-shirts. A company charges $5 per shirt. If you order less than 100 shirts, $4 per shirt between 100 and 300 shirts, and $3 per shirt if you order over 300. Write a piecewise function to represent this situation. So we are going to let f of x here represent the cost of the shirts. So how much is the shirt going to cost, where x is the number of shirts that are ordered. So start your piecewise function with f of x, and then equals, and then you're going to put a brace. Now this brace needs to be big enough so that I can have 1, 2, 3 different parts, because there's 3 different costs per different numbers of shirts. The first cost that I get to is $5 per shirt if I order less than 100. So it's going to be $5, I put a comma here, if I order less than 100. So that's all x values less than 100. I then switch to a new function. The shirts are not going to cost $5 after I get enough t-shirts. The cost is going to be $4 if we order between 100 and 300 shirts. That would include 100 shirts, and that would include 300 shirts. So since both of them are included, we're going to say 100 less than or equal to x less than or equal to 300. That's our mathematical way to say that x is between 100 and 300 and is included in both. And the shirt price changes again to $3 for all orders of over 300 shirts. So great, where x is greater than 300. This is a way that we represent this piecewise function. Number 8. You're making class tattoos for the pep rally. There's a $10 setup fee for the design. Think of this $10 as a constant. It's going to cost $10 no matter what. If you have 200 or less tattoos, the cost is going to be $1 per tattoo. That is variable. It changes depending on the number of tattoos. If you order over 200 tattoos, it's going to be 50 cents per tattoo. Write a piecewise function to show the price based on the tattoo. So again, we're going to create a piecewise function by saying f of x equals, and we need a brace. This is going to have to be big enough for 2 different types of orders. Okay, f of x is the price based on the number of tattoos, where x is the number of tattoos. So if I order 200 or less, right, that is less than or equal to 200, 200 or less. If I order 200 or less of these tattoos, it is going to cost me that setup fee of $10 plus $1 times the number of tattoos. $1 times x, which is just x, 1x or x. If you put a 1 there, it's okay, not a big deal. The $10 is always going to be part of the cost. For every tattoo, it's going to be $1. It changes to a different price structure for orders over 200. So when x is greater than 200, for over 200, we have a price structure that is still $10 for setup, but it's only 50 cents per tattoo, or 0.5 times X. Finally, number 9, you start tutoring elementary students in math and you schedule a month at a time. You charge $20 an hour for less than 3 hours and $15 for 3 or more hours. Write a piecewise function to show the rates based on hours and determine how much you would make if you tutored for 4 hours. So first, we kind of have 2 questions here. First, write a piecewise function. And second, determine how much money you would make if you tutored for 4 hours. So we'll start with the first question by putting f of x equals brace. And we have 2 different scenarios here. $20 an hour for less than 3 hours. So when x is less than 3, it's going to be $20 times the number of hours, where x is the number of hours. For 3 or more hours, that would be x greater than or equal to 3. For 3 or more hours, we charge less. It's $15 times the number of hours. So if I 3 hours would be 3 times 15. This question says, well, how much would it cost you for 4 hours? That would be f of 4, because x is the number of hours. Well, I have to make sure that I choose the right one, which is the bottom guy here, because 4 is greater than 3. So that would be $15 times 4 hours, which is $60. The last few examples that I want to talk about really quickly are called step functions. And they're called step functions because if you look at them closely, they kind of look like steps, like up, 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 up. So there's all these little constant bits. When x is between 0 and 1, y is equal to -3. When x is between 1 and 2, y is equal to -1. When it's between 2 and 3, it's equal to y is equal to +1. And then y is equal to +3 between an x value of 3 and 4. And again, I've used the open circles and closed circles for the boundaries that had less than or equal to, they got closed circles. And for the boundaries that included less than, they got open circles. So what is our domain? The least x value that we have is x equals 0. That's the least x value that we have is x equals 0. Even though the function jumps, there's no break in the domain because I go from 0 to just left of 1, but 1 is still covered. And from 1 to just left of 2, but 2 is still covered here. And 2 to just left of 3, but 3 is still covered. And I stop at 4. That's the highest that I go. Because it has an open circle, it's going to get a parentheses. So the function is constant here along an interval, or several intervals actually, which basically means that it's not increasing and it's not decreasing. It's just going left to right. In order to describe these intervals where it's constant, we're going to use x values or the domain. So we have a constant interval from 0 to 1. Now, it is not constant here at or through an x value of 1 because there's a point of discontinuity. It jumps up. So we're going to say that the constant interval is from 0 to 1. And there is another constant interval from 1 to 2. And there is another constant interval from 2 to 3. And yet another one from 3 to 4. And all of those are x values. 0 to 1, 1 to 2, 2 to 3, 3 to 4. Our final example today is another step function. It's a special type of piecewise function that looks like stair steps. Again, I've already graphed it using these x values and y values of -3, -1, 1, and 3. Okay. Very similar to the last one. Closed circles on the left for each of these steps. Open circles on the right for each of these steps. There are 2 ways that you can write the range here. Since we have y values of only -3, only -1, only +1, and only +3, You could try to write it in interval notation and it would look like this, but it's kind of clunky because it's really not an interval. We're not going from something to something else. We really have four different values that y takes on in this function. It is better in this case, since they are that way, to just list them out in a list, and we put braces around it. It's called a set, as a set of possible y values. The only four y values that are on this function are -3, -1, +1, and 3. There are 3 points of discontinuity. Remember, that's where there's a gap in the function. It behaves one way, jumps somewhere else, jumps somewhere else, jumps somewhere else. Those 3 jumps that we witness happen at x equals -3, x equals -2, and x equals -1. Well, there have been some new things today that we've had to talk about. Piecewise functions, a big deal, kind of cool. You have some practice, and as you're working through the practice, if you have questions, please ask me about them, and let's talk about it together. But I hope that you are successful and it all makes sense and that you do well. I'll see you in class.